Today we're going to talk about one specific operation that can be done with vectors and some of the applications of that operation. Specifically, we're going to be looking at what's known as the dot product. So I'm going to start by just giving you the definition. So I have written on the screen the definition of the dot product. So to find what we call the dot product of two vectors, we multiply their corresponding components together and then add those products. So we take the x components, multiply them together, plus the y components multiplied together. And if it's a vector in 3D, we would also take the z components, multiply them, and add that on. So the first thing I'd like to point out is that the dot product is a scalar. It's an operation that you do to two vectors that gives you a number that is not a vector. I also have on the screen a list of some properties of the dot product. I just like to draw attention to the first one. The first property says that the order that you multiply in doesn't matter. And then our other properties, we can come back to them later if we need to, but they really are just saying things that like we can distribute to sums. If we have a scalar, we can multiply the scalar by either vector and then perform the dot product. If we take the dot product with 0, we get 0, etc. So let's just do some examples and see how this works. So here's my first example. I have two vectors. Vector u is 3i minus j, and vector v is 2i plus 5j. We're going to find u dot v. Let's do that first. So to find my dot product, I'm going to take my vectors, 3, negative 1, and 2, 5, and I multiply the corresponding components together. So 3 times 2, and then I multiply negative 1 times 5, and I add those results together. So that gives me 6 minus 5, 1. So my dot product is 1. Again, I want to point out when you're computing a dot product, the answer is just going to be a number. The answer is not going to be a vector. All right, what about 2 times v dot v? I am going to start by finding v dot v. So vector 2, 5 dotted with vector 2, 5. 2 times 2 plus 5 times 5. So same process, I multiply the corresponding components together and add that result. I get 4 plus 25 is 29. Now earlier in one of my properties, I noted that when you take a vector and you dot it with itself, it is always going to give you the magnitude squared. That's just because you're actually squaring the components and adding them together. So I guess we could conclude that in this particular case, if v dot v is 29, then the magnitude of v has to be square root of 29. Now let's see, this problem wants us to find 2 times v dot v. So 2 times 29 is 58, and that's my final answer. Now, one use of the dot product is we can use it to find the angle between two vectors. Turns out that u dot v is going to equal the magnitude of u times the magnitude of vector v, so the length of those vectors, times the cosine of the angle between them. This formula actually comes directly from the law of cosines. I have a proof written out on the screen. Feel free to skip ahead. I'm not going to test you on this proof. I just wanted to show you where this formula comes from. But basically, you can create a triangle that contains vector u, v, and then you can connect those vectors with the vector v minus u. And you have a triangle, and then you can apply the law of cosines, do some simplification, and that's where this formula comes from. I'm more than happy to chat with any of you outside of class if you want to see this proof in a little bit more depth or want to talk to me about it. But let's focus on the things that we need to know for the course. So let's just do an example. Find the angle between vector u, which is 2, negative 1, 0, and v, 4, 1, negative 2. Give your answer in degrees rounded to the nearest tenth. So on the previous slide, we learned that u dot v equals magnitude of u times magnitude of v times cosine of theta. And so I just took that formula and I rewrote it in a slightly different form. I solved it for cosine theta. So cosine theta would be u dot v divided by magnitude of u, magnitude of v. So I'm going to go ahead and compute all of those quantities. So u dot v would be 2 times 4 plus negative 1 times 1 plus 0 times negative 2. So multiply the corresponding components, add them together, and I ended up getting 7. So my dot product is the number 7. And then I'm going to find the magnitude of each of those vectors. So magnitude of u would be the square root of the sum of the squares of the components. So square root of 2 squared plus 1 squared plus 0 squared. I got root 5. And then magnitude of v, square root of 4 squared plus 1 squared plus 2 squared. I got root 21 for that one. So plugging this into my formula, that means cosine theta equals 7 divided by root 5 times root 21. And so to find theta, I'm going to take the inverse cosine of 7 divided by, I just went ahead and wrote that root 5 times root 21 is root 105. This is not a common trig value. I don't have the angle memorized. I would have to use a calculator. So in my calculator, I entered inverse cosine of 7 divided by root 105. My calculator was in degree mode, and so my answer is 46.9 degrees. Again, that's the angle between those two vectors. Now I want to make one comment here while we're doing this problem. If you take a closer look at this formula, notice that if theta, if the angle between the vectors is 90 degrees, and you plug in 90 degrees into your formula, well, cosine of 90 degrees is 0, and that means u dot v is 0. So anytime the angle between your vectors is 90 degrees, we say that our vectors are orthogonal. It's kind of a fancy way of describing vectors that are perpendicular. So the vectors are orthogonal if their dot product is equal to 0. Okay, because cosine of 90 degrees is 0. Dot product is related to cosine of the angle between the vectors. So vectors are orthogonal if they have a dot product of 0. All right, the next thing I want to mention is when we're talking about vectors in space, so a three-dimensional vector like the one I have drawn on the screen, and we want to describe the angle that this vector makes with the origin. Unlike when we're working in the plane, in 2 dimensions, there isn't really a simple way to describe the angle of that vector. We can't really just give one angle of that vector. Instead, we're going to give what's called direction cosines, which are basically angles that describe the location of the vector relative to our coordinate axis. So relative, what is the angle to the x-axis, what is the angle to the y-axis, etc. So I'm going to define angle alpha to be the angle that between this vector, we'll call it vector v, and the x-axes. Using my dot product formula, cosine of angle alpha has to be vector v dotted with I hat. So I is our unit vector that points in the positive x direction, so along the x-axis. So cosine of alpha has to be v dotted with I hat divided by magnitude of v times magnitude of I. Now, because I is a unit vector, its magnitude is just 1, and vector I only has a component in the x direction. So when we take the dot product of v with I, we're actually just going to get the component of v in the x direction. So this is our definition of our first direction cosine. Cosine of angle alpha is our x component, which I'm calling v1, divided by the magnitude of v. And we can do something similar with the other axes. I'm going to define angle beta to be the angle between the y-axis and vector v. So using similar reasoning, cosine of angle beta, is our y component divided by the magnitude of vector v. And then finally, we'll say angle gamma is the angle between the z-axis and vector v. And again, using the same reasoning, using our dot product formula, we get cosine of angle gamma is the z component divided by the magnitude of v. So example 3, if I want to find the direction angles for vector v equals 4, 6, 1, first thing I'm going to do is find its magnitude. The magnitude of vector v would be the square root of 4 squared plus 6 squared plus 1 squared. Let's see, I got root 53. And so then what we call our direction cosines, I have written on the screen. Cosine of angle alpha is the x component, which was 4 over the magnitude, root 53. Cosine of angle beta is that y component, which was 6 over root 53. And then finally, cosine of angle gamma, z component, which was 1 over that magnitude. So those are my direction cosines. To find the direction angles, I'm going to have to take the inverse cosine of each of these ratios. I had to use a calculator again. My calculator is still in degree mode, and so I jotted down what I got. Inverse cosine of 4 over root 53 is 56.7 degrees. And again, that's an angle between the positive x-axis and this vector. Angle beta, I got 34.5 degrees. That's the angle between the positive y-axis and the vector. And finally, the angle between the positive z-axis and the vector, I got 82.1 degrees. So those are my 3 direction angles, which really just give us information about where exactly is that vector in space. All right, the next thing I want to focus on in this section, another kind of application of the dot product, is the idea of a projection. And so we're going to talk about the projection of one vector onto another. So first of all, on the screen, I have the notation that we're going to be using. So this is my notation for projection of vector v onto vector u. And so I have a picture drawn to try to illustrate what we're doing here, but the projection of vector v onto vector u is basically just the component of v in the direction of u. And so that's what we're looking at here in the picture. Maybe I'll kind of darken it in. So if I find the component of vector v in the direction of u, that is known as my projection. Another way of thinking about it is, what is the shadow that vector v makes onto vector u? A separate way of thinking about it. All right, so let's start by just drawing some projections. We're going to sketch projection of b onto a and projection of a onto b for the vectors shown in the image below. So first of all, it's kind of hard to see, but there's arrows. They didn't really show up at the end of these vectors. So let's start with what I have abbreviated proj AB. We read that as the projection of B onto A. So the subscript, the A, is what you're projecting onto. So projection of B onto A. So this is the component of B in the same direction of A. And so I went ahead and extended the line for vector A. I did that in blue. So I just extended it as far as I would need to make my projection. And then I went to the end of vector B, and I dropped a line down to vector A. Did that in green. And I dropped a line down that's perpendicular to A. And then I shaded it in red. This is the component of B in the direction of A, or my projection of B onto A. So it's the part of vector B that's in the same direction as A. So if we want to do it in the other order, projection of A onto B, I'm going to do something similar. In blue there, I just extended the line for vector B. That's what I'm projecting onto. So I just extended that as far as I needed it. And then I sketched the component of A, or the shadow of A, in the direction of B. And that is drawn in red. And so another way of thinking about that is I took the end of vector A, I just dropped it down to the blue vector B, and that's how I found my projection. So again, a projection is similar to a component. I kind of like thinking of it as kind of a shadow or a footprint. So you could think of it as B is the ground. And what kind of shadow would you have if the sun was directly overhead? So how do we compute projections? Well, here's a formula. Projection of V onto U is U dot V divided by magnitude of U squared times vector U. So the first thing I should mention is that when you're computing a projection, you're computing a new vector. The answer is a vector. But before we actually do some computations, let me show you where this formula comes from. This one isn't too hard to prove. So if you take a look at my picture, I have tried to draw in red the projection of vector V onto vector U. And I'm going to call theta the angle between those two vectors. Using trigonometry, just SOHCAHTOA, I know that the length of my projection, the length of that arrow in red, is equal to the length of vector V times cosine theta. That just comes directly from my SOHCAHTOA. Cosine theta is adjacent over hypotenuse. So the magnitude of my projection is the magnitude of V times cosine theta. My projection, though, is going to be a vector in the direction of U. So I'm going to take the magnitude of that projection and I'm going to multiply it by a unit vector in the direction of u. And so I'll circle it. My unit vector in the direction of u is u divided by its magnitude. So that's what our projection is. The magnitude of the projection times a unit vector in the direction of u. Let's plug some stuff in. We just figured out using trigonometry that the magnitude of our projection has to be magnitude of v times cosine theta. So I have magnitude v cosine theta u divided by magnitude of u. And then I went ahead and I replaced the cosine theta with that dot product formula. Cosine theta equals u dot v divided by magnitude u magnitude v. We can do some simplification and we end up with the formula that I have on the screen. Because the magnitude v's cancel out, we're just left with u dot v, and then on the bottom we have magnitude of u times magnitude of u. I'm going to write that as magnitude of u squared, and then still times vector u. All right, so that is how we're going to compute a projection of a vector onto another vector. And let's see how that works with an example. For the vectors A, which is 1, 2, 0, and B, which is negative 2, 0, 5, let's find the projection of B onto A. And so I'm going to copy down my formula with A's and B's. So projection of B onto A is A dot B divided by magnitude of A squared times vector A. So we're projecting onto A. That's why we're multiplying by vector A. So I'm going to go ahead and compute all of these components. Let's see, A dot B is 1 times negative 2 plus 2 times 0 plus 0 times 5. I got negative 2. And the magnitude of vector A is the square root of 1 squared plus 2 squared plus 0 squared, or root 5. So projection of B onto A would be negative 2 divided by root 5 squared, which just turns into a 5. So negative 2 fifths times vector A, which is 1, 2, 0. And then I'm going to go ahead and distribute my negative 2 fifths. And so my new vector is negative 2 fifths, negative 4 fifths, and 0. And that is a vector in the direction of vector A, so same direction as vector A, whose magnitude is the component of B in the direction of A. Let's do one more example. In this example, we are going to find the component of u onto v, and then the component orthogonal to v. So let's start by finding the component of u onto v. That's just another way of saying let's find the projection of u onto v. So I've jotted down my formula. I have to compute u dot v over magnitude of v squared times vector v. So u dot v, 4 times 5, plus negative 1 times 2, I got 18. And then magnitude of v would be square root of 5 squared plus 2 squared, so root 29. That means my projection is going to be 18 over root 29 squared, so 18 over 29, times vector v, which was 5, 2. And then I went ahead and I distributed the 18 over 29, and that gave me the vector 90 over 29, 36 over 29. So that's the first part of this problem. That's the component of u onto vector v. Now for the second part, we want to find the component orthogonal to v, perpendicular to v. So let me draw a picture to try to explain what's happening here. So we've got vector v, which is 5, 2, and vector u, which is 4, negative 1. We just computed the component of u onto v, which I have colored in purple. So that arrow in purple is the vector we just computed. The second part of this problem is asking us to find the vector that I'm going to call w, that I have drawn in my picture in red. The component of u, it's perpendicular or orthogonal to vector v. And so looking at my picture, one thing I notice is if I take the purple arrow plus the red arrow, it should add up and give me vector u. If I take my component parallel to v plus my component perpendicular to v, they should add up and give me u. So my projection, which was 90 over 29, 36 over 29, plus vector w, has to equal vector u, which was 4, negative 1. So I can just solve for w by subtracting. Vector w would have to be the vector 4, negative 1 minus 90, 29, 36, 29. And I just subtracted the corresponding components and got 26 over 29, negative 65 over 29. So I'm going to finish by doing one more application of the dot product, and that is the concept of work. And so work gives information about when a force is applied to move an object. You'll probably talk about this concept in more detail in a physics class. In this class, I really just want to focus on how we do the computation. How can we actually use vectors and calculus to compute work? And so here's my definition. If we have a constant force applied to an object, so it moves in a straight line path from P to Q, the work done by force F on that object, which we'll say is acting at angle theta from the line of motion, is given by F dot PQ. So the idea is to compute the work required to move an object. We're going to take the force applied to the object, dotted with the path the object is moving in. And then this is my dot product formula. That dot product is magnitude of my force times magnitude of vector PQ times cosine theta. So that's my same formula, my same dot product formula, just written with different letters. So here's an example. To close a sliding door, a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees. Find the work done in moving the door 12 feet to its closed position. So here's kind of a picture of what's happening. We have this sliding door, and so I guess based on my picture, I'll darken in, there's my door in black, and the idea is the door is going to slide closed, and we are pulling a rope with this force of 50 pounds to close that door. Find the work done in moving the door 12 feet to its closed position. So to find the work, we're going to take the dot product of vector F with vector PQ. And so I think the easiest way to find this dot product is to use that formula with the cosine. So the magnitude of vector F is 50, where our force is 50 pounds. The magnitude of vector PQ is the 12 feet. We're moving that door 12 feet. And the angle between those vectors is that 60-degree angle. So I just have to take 50 times 12 times cosine of 60 degrees. And I ended up getting 300. And so that's the work that we have done here. I guess since we multiplied pounds by feet, my units would be foot-pounds. We'll talk more about the idea of work later on in the course. So we're definitely going to have to use calculus if our force isn't constant, or if we're not moving that object in a straight line path. Those are some things that we're going to think about and eventually solve later on in the course. All right, that's it for this lesson. Please let me know if anything was unclear.